Hello friends, as we learnt in our previous discussions that flip-flops can be connected together to perform counting operations. So, such a group of flip-flops is a counter. The number of flip-flops used and the way in which they are connected determines the number of states and also the specific sequence of states that the counter goes through during each complete cycle. Counters are classified into two broad categories, asynchronous and synchronous, according to the way they are clocked. In asynchronous counters, commonly called ripple counters, the first flip-flop is clocked by the external clock pulse, and then each successive flip-flop is clocked by the output of the preceding flip-flop. In synchronous counters, the clock input is connected to all of the flip-flops so that they are clocked simultaneously. Within each of these two categories, counters are classified primarily by the type of sequence, the number of states, or the number of flip-flops in the counter. Asynchronous counter operation. The term asynchronous refers to events that do not have a fixed time relationship with each other and generally do not occur at the same time. An asynchronous counter is one in which the flip-flops within the counter do not change states at exactly the same time because they do not have a common clock pulse. Figure shows a 2-bit counter connected for asynchronous operation. Notice that the clock is applied to the clock input C of only the first flip-flop, flip-flop 0, which is always the least significant bit. The second flip-flop, flip-flop 1, is triggered by the Q0 bar output of flip-flop 0. Flip-flop 0 changes state at the positive going edge of each clock pulse, but flip-flop 1 changes only when triggered by a positive going transition of the Q0 bar output of flip-flop 0. Because of the inherent propagation delay time through a flip-flop, a transition of the input clock pulse and a transition of the Q0 bar output of flip-flop 0 can never occur at exactly the same time. Therefore, the two flip-flops are never simultaneously triggered, so the counter operation is asynchronous. Timing diagram. Let's examine the basic operation of the asynchronous counter by applying 4 clock pulses to the flip-flop 0 and observing the Q output of each flip-flop. Figure here illustrates the changes in the state of the flip-flop outputs in response to the clock pulses. Both flip-flops are connected for toggle operation, that is j is equal to 1 and k is equal to 1, and are assumed to be initially reset, that is low. The positive going edge of clock 1 causes the Q0 output of flip-flop 0 to go high. At the same time, the Q0 bar output goes low, but it has no effect on flip-flop 1 because a positive going transition must occur to trigger the flip-flop. After the leading edge of clock 1, Q0 is equal to 1 and Q1 is equal to 0. The positive going edge of clock 2 causes Q0 to go low. Output Q0 bar goes high and triggers flip-flop 1, causing Q1 to go high. After the leading edge of clock 2, Q0 is equal to 0 and Q1 is equal to 1. The positive going edge of clock 3 causes Q0 to go high again. Output Q0 bar goes low and has no effect on flip flop 1. Thus, after the leading edge of clock 3, Q0 is equal to 1 and Q1 is equal to 1. The positive going edge of clock 4 causes Q0 to go low, while Q0 bar goes high and triggers flip flop 1, causing Q1 to go low. After the leading edge of clock 4, Q0 is equal to 0 and Q1 is equal to 0. The counter has now recycled to its original state, that is, both flip flops are reset. In the timing diagram, the waveforms of Q0 and Q1 outputs are shown relative to the clock pulses. For simplicity, the transitions of Q0, Q1 and the clock pulses are shown as simultaneous, even though this is an asynchronous counter. There is, of course, some small delay between the clock and the Q0 transition and between the Q0 bar transition and the Q1 transition. Note in figure that the 2-bit counter exhibits 4 different states, as you would expect with 2 flip flops. Also notice that if Q0 represents the least significant bit and Q1 represents the most significant bit, the sequence of counter states represent a sequence of binary numbers as listed in this table. Since it goes through a binary sequence, the counter in figure is a binary counter. It actually counts the number of clock pulses up to 3, and on the 4th pulse it recycles to its original state, that is, Q0 is equal to 0, Q1 is equal to 0. The term recycle is commonly applied to counter operation. It refers to the transition of the counter from its final state back to its original state. A 3-bit asynchronous binary counter. The state sequence for a 3-bit binary counter is listed in table, and a 3-bit asynchronous binary counter is shown in here. The basic operation is the same as that of the 2-bit counter, except that the 3-bit counter has 8 states due to its 3 flip flops. A timing diagram is also shown in figure for 8 clock pulses. Notice that the counter progresses through a binary count of 0 through 7 and then recycles to the 0 state. This counter can be easily explained for higher count by connecting additional toggle flip flops. Propagation delay. Asynchronous counters are commonly referred to as ripple counters because the effect of the input clock pulse is first felt by flip flop 0. The effect cannot get to flip flop 1 immediately because of the propagation delay through flip flop 0. Then there is the propagation delay through flip flop 1 before flip flop 2 can be triggered. Thus, the effect of an input clock pulse ripples through the counter, taking some time due to the propagation delays to reach the last flip flop. Asynchronous decade counters. The modulus of a counter is the number of unique states through which the counter will sequence. The minimum possible number of states, that is, maximum modulus of a counter, is 2 to the power n, where n is the number of flip flops in the counter Counters can be designed to have a number of states in their sequence that is less than the maximum of 2 to the power n. This type of sequence is called a truncated sequence. One common modulus for counters with truncated sequence is 10, called mod 10. Counters with 10 states in their sequence are called decade counters. A decade counter with a count sequence of 0 through 9 is a BCD decade counter because its 10 state sequence produces the BCD code. This type of counter is useful in display applications in which BCD is required for conversion to a decimal readout. To obtain a truncated sequence, it is necessary to force the counter to recycle before going through all its possible states. For example, the BCD decade counter must recycle back to the 0000 state after the 1001 state. A decade counter requires 4 flip-flops. Let us use a 4-bit asynchronous counter such as the one shown here and modify its sequence to illustrate the principle of truncated counters. One way to make the counter recycle after the count of 9 is to decode count 10 with a NAND gate and connect the output of the NAND gate to the clear inputs of the flip-flops. Notice in figure that only Q1 and Q3 are connected to the NAND gate inputs. This arrangement is an example of partial decoding in which the two unique states Q1 is equal to 1 and Q3 is equal to 1 are sufficient to decode the count of 10 because none of the other states 0 through 9 have both Q1 and Q3 high at the same time. When the counter goes into count 10, the decoding gate output goes low and asynchronously resets all the flip-flops. The resulting timing diagram is shown in figure. Notice that there is a glitch on the Q waveform. The reason for this glitch is that Q1 must first go high before the count of 10 can be decoded. Not until several nanoseconds after the counter goes to count of 10 does the output of the decoding gate go low. Thus, the counter is in the 1010 state for a short time before it is reset to 0000, thus producing the glitch on Q1 and the resulting glitch on the clear bar line that resets the counter. Synchronous counter operation. The term synchronous refers to events that have a fixed time relationship with each other. A synchronous counter is one in which all the flip-flops in the counter are clocked at the same time by a common clock pulse. Figure shows a 2-bit synchronous binary counter. Notice that an arrangement different from that for the asynchronous counter must be used for the J1 and K1 inputs of flip-flop 1 in order to achieve a binary sequence. To understand the operation, we assume that the counter is initially in the binary 0 state, that is, both flip-flops are reset. When the positive edge of the first clock pulse is applied, flip-flop 0 will toggle and Q0 will therefore go high. What happens to flip-flop 1 at the positive going edge of clock 1? To find out, let us look at the input conditions of flip-flop 1. inputs J1 and K1 are both low because Q0 to which they are connected has not yet gone high. Remember, there is a propagation delay from the triggering edge of the clock pulse until the Q output actually makes a transition. So, J is equal to 0 and K is equal to 0 when the leading edge of the first clock pulse is applied. This is a no change condition and therefore, flip flop 1 does not change state. After clock 1, Q0 is equal to 1 and Q1 is equal to 0, which is a binary 1 state. When the leading edge of clock 2 occurs, flip flop 0 will toggle and Q0 will go low. Since flip flop 1 has a high on its J1 and K1 inputs at the triggering edge of the clock pulse, the flip flop toggles and Q1 goes high. Thus, after clock 2, Q0 is equal to 0 and Q1 is equal to 1, which is a binary 2 state. When the leading edge of clock 3 occurs, flip flop 0 again toggles to set the state and flip flop 1 remains set because its J and K inputs are both low. After this triggering edge, Q0 is equal to 1 and Q1 is equal to 1, which is a binary 3 state. Finally, at the leading edge of clock 4, Q0 and Q1 go low because they both have a toggle condition on their J and K inputs. The counter has now recycled to its original state, that is binary 0. The complete timing diagram for the counter is shown in figure. Notice that all the waveform transitions appear coincidental, that is, the propagation delays are not indicated, although the delays are an important factor in the synchronous counter operation. In an overall timing diagram, they are normally omitted for simplicity. Major waveform relationships resulting from the normal operation of a circuit can be conveyed completely without showing small delay and timing differences. However, in high-speed digital circuits, these small delays are an important consideration in design and troubleshooting. A 3-bit synchronous binary counter. A 3-bit synchronous binary counter is shown in figure A and its timing diagram is shown in figure B. You can understand this counter operation by examining its sequence of states as shown in table. First, let us look at Q0. Notice that Q0 changes on each clock pulse as the counter progresses from its original state to its final state and then back to its original state. To produce this operation, flip flop 0 must be held in the toggle mode by constant highs on its J0 and K0 inputs. Notice that Q1 goes to the opposite state following each time Q0 is a 1. This change occurs at clock 2, clock 4, clock 6 and clock 8. The clock 8 pulse causes the counter to recycle. To produce this operation, Q0 is connected to the J1 and K1 inputs of flip flop 1. When Q0 is a 1 and a clock pulse occurs, flip flop 1 is in the toggle mode and therefore changes state. The other times when Q0 is a 0, flip flop 1 is in the no change mode and remains in its present state. Next, let us see how flip flop 2 is made to change at the proper times according to the binary sequence. Notice that both times Q2 changes state, it is preceded by the unique condition in which both Q0 and Q1 are high. This condition is detected by the AND gate and applied to the J2 and K2 inputs of flip flop 2. Whenever both Q0 and Q1 are high, the output of the AND gate makes the J2 and K2 inputs of the flip flop 2 high, and flip flop 2 toggles on the following clock pulse. At all other times, the J2 and K2 inputs of flip flop 2 are held low by the AND gate output, and flip flop 2 does not change state. So friends, that brings us to the end of our discussion in this lecture, and therefore we sum up. Counters are classified into two broad categories, asynchronous and synchronous. Asynchronous means that each flip flop after the first one is enabled by the output of the preceding flip flop. A modulus 14 counter has 14 states requiring 4 flip flops. In synchronous counters, the clock input is connected to all of the flip flops so that they are clocked simultaneously. The counter can be preset or initiated to any given state. So, that is it for today. See you in the next lecture with more on counters. Thank you very much.